Yeah. So what I was saying is, if you recall, if you see, the game definition is deterministic, right? So the game's definition. The game normal form game comes with a number of players, set of players. Strategy, action profile space. This is, and this utility function. Right. The issue is that the players are not just restricted to playing a pure strategy, which is basically a choice of action from AI. They can play a randomized strategy, which is basically a distribution over the actions available to them. So, in the player I has a set of actions available to him, which is given by the set AI, capital AI, right. Player I has, I chooses action from AI, right. This is what constitutes pure strategy. When he chooses not one action, but a probability distribution over an action, over this action space, that is what is called a mixed strategy. So, the question is, if we accept that mixed strategies are a valid way of playing the game, then there has to be a reasonable way of computing the payoff resulting from that strategy. Okay. So, that payoff, because the strategy is randomized, right, chooses action. So, this is called this is the pure strategy, choice of one single action. Okay. A mixed strategy, I chooses a distribution over AI. This is a mixed strategy. I is mixed strategy, right, and the utility. So, when each individual chooses their action, what you get is this action profile, right, which is basically an element of this set, product space, right. Yes, no, this is I am talking, this is a pure strategy, right. A pure strategy for each of the individual player taken together constitutes a pure strategy profile. Okay. So, this is would be a I tried to be, or let us say, or action profile. Okay. Similarly, a mixed strategy profile would be a distribution over this set, which is basically that's you. This is actually not the notation, but okay, fine. This is a mixed strategy profile, where each x1, x2, so on to xn, each represents a mixed strategy. X1 represents the mixed strategy of player 1, x2 is a mixed strategy of player 2, and so on, right. And the point is, so what is a mixed strategy? It is just a distribution over the sort of the respective action spaces, right, action set or action space. So, that is what this is. So, you take x as an element, it is basically you can think of the distribution itself as a vector of with ai number of this many number of coordinates, because think about a distribution, it can be written as a stochastic vector, right. So, each point here corresponds what is the probability x, the distribution x gives to the action A. That is what this is, x of A. Sometimes it will be written as x subscript small a, I am choosing to write it this way. So, so x is a distribution over ai, over the set capital AI, okay. And if I look what does distribution mean, a probability distribution is basically valuation over all possibilities where all those values are non-negative, cannot exceed 1 and they all add up to 1, right. So, that is what this is. Any distribution over the action space corresponds to a mixed strategy, and a mixed strategy by definition is a distribution, that is it, okay, 1 to 1. So, the question is, if we accept that this is the acceptable sort of a strategy, valid strategy, then the players have to be able to understand, analyze their payoff resulting out of playing such a strategy, right. Utility function takes is defined over this product space, like everybody plays their own action, right, pure strategy, and you get a real valued number. It could be negative, positive, whatever, but it is a real valued number. Similarly, the payoff of a of a mixed strategy profile is an expected value over what is that random variable over which we are computing. That is the sort of a subtle thing, okay. The point is that when I sample, so every player finds a distribution from their mixed strategy space, okay, delta I. Now, and that together constitutes a mixed strategy profile. This is it, right, x. So, you choose x1, I choose x2, she chooses x3, Lalit chooses x4 and things of that nature. Together it is a mixed strategy profile. Now, the question is, so I was denoting this as, I believe, let us continue to use that, I will explain what it, payoff of mixed strategy profile x bar, okay. For this we are denoting like this, it is all possible, okay, let me write this first and I will tell you. By, let us call it this. Do you remember what I was using as the notation wise? You are
it was for like payout was like each player at a time.
What am I? No, that is fine. I just want to be consistent with the notation. You are. Sorry, of course. I don't know why. I already have introduced it. Yeah. Okay. This is it. So let us take a small example. Head and tails, okay, or okay, rock paper scissors. It has 3 options, okay. So I play a mixed strategy. The mixture is over the 3 possibilities that are open to me, rock paper scissors. You also to play the same thing, right. You have the exact same 3 options. Now our probability distribution may be the same or different, right, meaning I decide to put different values, different mass on each of the individual choices you from what you have chosen, okay. So that defines a different distribution altogether. The point is, this sort of a summation, what are we actually doing? We are basically seeing that the mixed strategy I have chosen and the mixed strategy you have chosen, this enumerates all possible action profiles. So, rock rock, rock paper, paper rock, rock scissor, scissor rock, and all possibilities, right, 3 times 3 if it is just a 2-player game, correct. So, that is what this is enumerating over, and we are saying under this probability distribution profile, which has the probability distribution of me, of mine and yours, right, what is the probability that this one particular choice of profile is actually realized, times the utility player payoff for player I. Okay. So, player I's payoff when mixed strategy profile x bar is played is this. So, I use the utility function of I, applied it to the choice vector a hat, right. So, basically it will be a summation over 9 possibilities, enumerating all possibilities. The utility value is whatever the utility value is. You and I both play rock, well it gives 0 to nobody wins anything. I play rock, you play paper, so I guess paper wins over rock, so you get something, I do not get anything, and so on and so forth, right. And if it switches, I win, so on, right. So, you can take I to be either me or you, and we can individually compute this. So, the question is how do we compute this value, that probability that this particular choice, take anything rock and paper, right, is realized by this distribution x, this mixed strategy profile x. It is basically computed by with an sort of assumption in mind that we are in a non-cooperative setup and everybody is playing independently, right. You have chosen your mixed strategy profile independently of me. So, whatever you have chosen there, what is the probability, the distribution you have chosen, the probability that it results in rock times the probability that the choice that I have chosen, the distribution, what is the value that distribution puts on my choice, correct?
So, it is the product of
Yes. So, this is the chalk a problem. So, let us write a hat. When I write like this, it means assume by default this is the notation. Okay. So, it is basically, I will not write probability here anymore, it is basically AI, yes. Okay. So, now I is this clear? This is saying what is the probability that the ith player has actually in the mixed strategy profile of the ith player, that is given by this xi vector, what is the probability that action AI is chosen. This means we are talking about the realizability of the action profile A1 to AN, okay? And we are summing over, meaning I am trying over all possible action profiles, okay? This is what this is. So, this is the definition of a, so this is a expectation, this thing nothing very particular. It really just depends on how we visualize this game, that a mixed strategy is a valid strategy to play the game, and then utility, how can we sort of infer the utility function in a way that makes sense for when players are playing mixed strategies, and what should be the their payoff when mixed strategies are played, not just by them, but potentially others as well. Okay. So, this was the basic. Okay. Any questions, any of you who are attending over Zoom, please let me know, please stop and just speak out. Okay. 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 All right. So, let us get started. Is that the only? Okay, let me just, yeah. So, this notation should not cause confusion, but still let us just be careful. Okay. This I is this I, okay, payoff of that player I. This is a product over all the players. Okay. So, this is the thing. Okay. So, now what is it? So, we ended yesterday's class with a proof of Nash's theorem, which said that Nash equilibrium for a finite game, a Nash equilibrium always exists. A finite game means finite players and finite strategy space, finite action space. Okay, this AI set is finite. Okay, that's the thing. Okay. Now, so the question is, whenever we have a nice concept like this, and I have already told you Nash equilibrium has been as a concept has been extremely influential in the growth of the subject and sort of well beyond this subject of game theory. Okay. So, now naturally the question is it exists, we understand, but how to compute it. Okay. So, that will be the topic of the general computational complexity of Nash equilibria will be the sort of subject of talk of our classes from next week onwards. We will see that it is basically believed to be intractable, like efficiently we do not think we can compute a Nash equilibria of an arbitrary finite game. Now, do you think it should be NP? What is that notion of intractability? Do you think it should be something like NP completeness or something? What else? No, when we say the Nash equilibria always exists, we mean mixed strategy Nash equilibria. So, clearly one thing about NP problems such as that are discussed under NP hardness and NP completeness is they are decision questions. They have a yes no answer. Does such a solution exist? And the answer has to be yes or no. That is the notion of, that is the template, those are the type of problems that are studied under NP completeness theory, right, or NP hardness theory. Okay. So, the point here is, the first thing you can see that there is a syntactic and as well as a semantic difference here. We are already saying a mixed strategy Nash equilibria always exists. So, it is no longer a decision question of yes and no. Question really becomes computing it. I mean, I said it as such that it exists. Now, the question is how to compute it. So, therefore, it does not quite fall into the framework of NP completeness theory or any other sort of complexity class that you know that is associated with yes no decision questions. Okay. So, we need to have a different kind of a complexity class which captures these sorts of questions, and we will hear about them more formally from next week onwards. I will also say that I am going to share a video in my later today or tomorrow about some we had a nice sort of a very overview talk on this during the recently concluded ACM school on game theory. So, you can hear it. It is not a formal description of what is to come, but it will give you a nice juxtaposition and a compare and contrast between various kinds of problems that we come across and what kind of computational complexity question we can ask. Okay. So, that is just watch it before next week's class. Now, to get back to this, I said that in every finite game it exists, and I am saying to you as a sort of just to reveal the truth, which is that in an arbitrary finite game we are not always, we do not believe it can be computed efficiently, but there are special categories of games, special class of games where it can be computed efficiently, and so that is what we will be talking about today. Okay. All right. So, the first such a class so I am going to run let's write it. So, when we say efficiently computable, what do we usually mean, by the way? What does efficiency mean? Louder? Polynomial in what? Somebody say. Shubhaman, you were saying something?
Yeah, I'm saying there exists a polynomial time algorithm to find the Nash equilibrium.
Okay, polynomial in? Satyam?
Input size.
Okay, okay. Polynomial in input size. An interesting point here is, we'll talk about this a bit later when we get to it, but it's some food for thought, okay. We are dealing with numbers here, functions here. The utility is real valued, right. So, when we say, so basically how we encode this function comes into play, right, because here the input consists of what? Some number of players. Okay, this can be done in log n bits if there are n players, right. Action also, I said it's a finite game, so each AI has some known finite bound, right. So, you can sort of list out each of the, like AI can be encoded in log cardinality number of bits, and with each of those values you can associate an action and so on and so forth. The question is the utility function representation and so on and so forth, right. So, like those are some of the things that we should sort of keep in mind. Now, let us talk about some special class of games, and we talked about some games in the very first class, one of which was let's write efficiently. The first class is the most basic fundamental need to have a game is at least 2 players, right. So, 2 player games, okay. Now, in 2 player games also, if we have a very general game which involves 2 players, that too can be hard, okay, and we will try to quantify exactly what kind of 2 player games actually we know to be hard, okay. But the special category of 2 player zero sum game, remember what zero sum games are, anybody? Some of whose okay, some of the utilities of the players is it some of the utilities across what? For any action profile, sum of UIA, right?
Over I.
Yes, is 0, correct, right. It's very self descriptive, it's zero sum game. The utilities add up to 0. For this, we know this is a polytime algorithm, okay. Now, interestingly, this has a very nice history. This result was known long before the start of game theory as a subject, formal subject like as we understand it today, is usually pinned to the publication of very influential book of economic theory of games and economic behavior by John von Neumann and Oscar Morgenstern. But von Neumann proved this, the thing that we will talk about 20 years before, but he was sort of thinking in exactly precisely what context he was thinking, it is not clear, but he basically had this result which later on was sort of recast in the way that we now know it. Okay, so, this is a polynomial time algorithm. In general, 2 player games hard, okay. I will say what kind of hard now. There are, okay. So, tell me, so if 2 player zero sum game is easy, what do you think is the situation with multiple player zero sum games? Should it be easy, should it be computable in polynomial time, or should it also be hard?
the general two-player games is hard. Multiplayer zero-sum game.
Let's call it n player, okay? N player zero sum game. What is it? You were saying something?
If this is easy, maybe we can convert general two-player games into multiplayer zero-sum games.
Okay, you're saying that if I know this to be hard, I will give a reduction from here to this to a n player zero sum game. Okay, yeah, if you knew this was hard, then starting with a hard problem, there should be a notion of reduction that would tell you that this problem is at least as hard as this, right? Reduction as we understand it. Okay, let me just pause and ask, how many of you are familiar with reductions? The kind where by which we, I'm talking to the people on over Zoom. I see some undergraduate students, so I'm asking. There are some undergraduate students, right? Okay, so specifically the, okay, all right. So he, Satya is suggesting that we should be able to show that if n player zero sum game is easy, is polynomial time solvable, then that should allow us to solve a general two-player game as well. That's what your recipe is, boils down to.
Yes.
Okay, all right. Can you suggest such a thing? Like, do you have a reduction in mind?
For third player, I can define some action, and for every and utility function can be like negative of the total of utility.
Okay. Okay. Yes, that's basically the idea, but we don't necessarily start from a general two-player game. What we start is the general n-player game. That we know is hard. Okay. So the point is, if n-player, any game, right, if this were easy, if an n-player zero-sum game were easy, meaning it was solvable in polynomial time, I can take any game which is not a zero-sum game, just an n-player game, n-player finite game, add an additional player whose utility basically is something that is sum of everybody's, and then put a negative on that, so that it artificially becomes a zero-sum game, and he has no, basically does not affect the game at all. So it's a fictitious player, let's say, who is just there to make the utility add up to 0, right? So whatever Nash equilibria you would get for this zero-sum game would also be a Nash equilibria for that original game. So therefore, it shouldn't be easy to compute an Nash equilibria for this game. I mean, it's a proof sketch, but it's basically the same idea. You can work out the detail exactly what the additional, that fictitious player is doing. His job is basically take any arbitrary n player game and convert it into an n plus 1 player zero sum game, right? Now, if this were actually, here n is just a place variable, right? I say n or n plus 1 does not make a difference. If this were actually polynomially times computable, then I could now find a Nash equilibria for this n plus 1 player zero sum game, and that fictitious player's role is he does not impact the profile, the strategy and the utility of anybody else. Like, his presence does not impact them in any way. He is just there to add up so that the utility becomes 0. Therefore, any Nash equilibria here would also be a Nash equilibria there, and a Nash equilibria there would also be a Nash equilibria here. Okay, that's a simple argument showing. If you try to figure this out, else I'll give a homework question with some hints, and you can see this. Okay, all right. This is also hard. So basically hard. The moment it is 3 or more, it becomes hard. Okay. Now there might be other things thrown into the game with more properties that makes the problem tractable again, but when we say like this, what we mean is a general category arbitrary game. Okay. All right. Okay. Now, there is something about this n player zero sum game, some special category of n player zero sum game where we basically get tractability back. N player or separable zero sum game. So, what does separable mean? Product of the utilities.
Some will individual utilities functions and
Yes, basically that's what the name is. So, you have n players, but the whole game basically decomposes into these smaller games where each player is playing these zero sum games with a subset of those n minus 1 players. Okay, the whole game may contain whatever hundreds of players, let's say, but the way the game space is structured, every player is basically playing a zero sum game with one other player. So, let's say four of us are playing a game. Okay, so the entire, while it involves 4 players, the payoff matrix and all the utility values are such that the entire payoff I get from playing this game with three additional players is basically the summation of the zero sum game I play with you, another 2 player zero sum game I play with you, another zero sum game I play with you, and this is the case with each of us. Okay, that's what a separable this thing means. Now, I am going to define this when we get to it. Okay, so let me, before we get to the proof of this, I am going to give a proof idea for this 2 player zero sum game. Okay, and then we will use some of the machinery to make sense there. This is part of the reason why, even though you have n players, but because it has these small basically 2 player zero sum games that are happening, that gives us enough structure to get a polytime algorithm. Okay, and the polytime algorithm basically again uses the same framework or LP duality. Okay, so rather this one uses LP duality, that one uses linear programming to give the polynomial time algorithm. Okay, we will also later on in the course we will also see another alternate proof of this result, and there are multiple proofs different people have there. This is one result that sort of keeps that people keep rediscovering at different forms and so on. So, but now we will discuss the 2 player format using LP duality, and then we will sort of extract some learning from there and apply to other things. Okay. Now, quickly before we go there, I want to say just n play, what do you yeah. So, we already saw so n player separable game. Okay, this is again hard. Okay, if you have an n player game which is separable, so the game that we were playing among each other was not a 2 player zero sum game. So, what it is, separability means that all these n players are basically engaged in these smaller games between 2 by 2. Okay. So, if suppose that is happening, smaller games are being played, but it is not zero sum game, it is some other arbitrary value game. Okay. Or this separability does not necessarily just have to be the smaller game does not necessarily have to be between 2 players, it could be a 3 player game, 4 player game, and so on and so forth. Okay. So, this n player separable zero sum game here, the kind that we are talking about is when the smaller games are between 2 players each. But if you have separability, but you have a more non zero sum game, but and possibly with more players, then it becomes hard again. Okay. So, so I do not know if we will get to this one, but these things we will see. Okay. So, let us start with the 2 player zero sum game. Yeah, but this is general game. I did not assume anything about separability and all. Yes.
Then it is two-player separability, meaning it is two-player general game.
Yeah. So that's why I'm saying, like, the any time the separability might be. So separability does not necessarily restrict the size of the game. If you are separable and into two-player games, and each of them is non-zero sum game, then those sub games itself are hard, right? Now imagine each of those sub games is not a two-player game, it's a large number of player game, but they are still easy, right? So what we are losing is, if you remove any of this two-player zero sum game, this thing, if you lose in it, you might just lose the polytime solvability. Okay, that is the thing. Okay, all right. Yeah. Okay. So we are now going to focus two-player zero sum game. Okay. I might have to delete that. You are taking pictures, no, Mohana? Yeah, take pictures and show me, otherwise I will forget what exactly. It reminds me all this because the videos are not ready right away. Okay, all right. Okay, so this part is really nice. So what happens is the following thing. Okay, so we are talking about two-player zero sum games, two-player games. So we will associate the utility function. Basically, we will write it in a matrix. It's a two-player thing, so I can write the utility function in a matrix, right? So let's call this the A matrix. The number of rows here is basically associated with the number of actions available to player 1. Okay, so the player 1 would be called the row player. It just helps remembering this thing, and the second player is the column player. Okay. So the number of rows tells you how many actions are that AI set corresponding to player 1. The number of columns associated with this matrix is in correspondence with the number of actions available to the second player. They may or may not be equal. Okay. Each position here, so Aij is basically the utility function of agent I, agent 1, let us say, the row player is agent 1, okay, let us just have this thing, when he is playing action I and the second player is playing action J. Is it okay? I am going to write it column I and J, okay, no need for. I said, right, each of the rows represent action available for row player, right. Each of the columns yes, but it is a zero sum game. So it means the payoff for the second player or the column player should be just the minus of this, right. So this is why it can be very compactly represented, just one matrix is enough, because it is a zero sum game, right. Otherwise we would have to have, like previously what were we doing, we were writing 2 entries in the entry space and so on. We do not have to do any of this because it is understood that it is a this thing. So actions for column player, okay. Keep this in mind, this picture is important, okay. So this is basically telling me utility for row player. So think about this A matrix as the payoff matrix for the row player, okay. So utility for row player when he plays I is the index of the row, okay, action I, and column player plays J, okay. This means that the payoff or the utility, I am using different words, I am just going to stick with this. utility for column player when row player plays I and column player plays j is equal to minus aij. Okay, lots of a's moving around. Should we convert this to capital P maybe, so that there is a pair of, there are so many a's here. Okay, so let us just convert it to small p. Okay. All right. So now, is this clear? Okay. Now tell me, in this setup, in this framework of a matrix, okay, and how do I represent a mixed strategy? Anybody on attending online? How do I represent a mixed strategy in this framework? Okay, let me help you. So we agreed that each of the individual rows represent the actions available to the row player. Each of the columns represent an action available to the column player, right? So mixed strategy is nothing but a distribution, a probability distribution over one's action, available actions. So for a row player, that would mean a probability distribution over this row set. So for a column player, it would be a probability distribution over the column set, right? Now what does that mean? It means a probability distribution is just but a small fractional mass, probability mass, we associate with every possible choice, each possible choice, right? So it means that with each row I am associating some value which is between 0 and 1. You could include 0 as well as 1, right? Another value associated with the second row and so on, such that they all add up to 1, right? That is basically what a stochastic vector would be, that adds up to 1. That is also called, that is a distribution, probability distribution vector also, and so on. There are different ways of calling these things, but that is what this would be, right. So a mixed strategy for row player is nothing but a x vector. Okay, I am going to slightly previously when we were using xi's, we were talking about the probability distribution for the ith player. Okay, now we are talking about two players, so bear with me. I am just going to use x and y to represent the mixed strategy for column player and the row player. Okay. Yeah, it should be m. Yeah, that's what. So standard linear algebra notation apply. Okay. So usually when we associate this thing vectors, we write them vertically. So what this is basically an x transpose vector. Okay. And y is, so if I should write it precisely depending on this thing, it should basically think of y as this, okay, as a column vector. As of now, just let me write it this way. No, I do not want to get distracted by like obvious notational issues. So what is happening here is, all we need is for these things to add up to 1. Let us use j maybe. Is this okay? This is what a mixed strategy for a row player would be, and this would be a mixed strategy for a column player. Okay. The way to interpret this is, the value that is stored here, let me write xi belongs to this closed interval 0 and 1. Okay. Everybody knows this notation, I think. So, x1 represents the probability by which row player will play row 1, x2 is probability by which row player will play row 2 and so on. Similarly, for column player, y1 represents the probability by which column player will play column 1, etc. Okay. So, now can you tell me, so we agree this is the notation here. So, what should be that quantity, the expected payoff of, let us say, row player when row player is playing strategy X and column player is playing strategy Y. So, expected payoff for row player when the mixed strategy profile X and Y is played. So, row player, so this notation means row player is playing X, I can put a vector sign here, and column player is playing Y. Okay. So, how do I what is the mathematical expression for this? So, louder, Satyam.
Guess is that it is p into x.
What is p?
Pk of matrix.
Okay, p into x. This x bar. Okay, what about y bar? Because we know that the payoff for the row player cannot just depend on what he is playing. It also depends on what the column player is playing. After all, this is a game, right? Over there also, these people were affected, player I was affected by what all the other individuals were playing, right. This is the probability of playing a particular action, right, and this was the utility. This utility function is defined over the this action profile space, right. So, here I will write it in case if somebody wants to answer this, they can say, but it should be x transpose A y, this vector. What does this mean? See, so this is the row vector x, sorry, this is not A, payoff matrix, right. This is the payoff matrix. This has m entries, it has m rows, n columns multiplied by, this is the y column vector, right. So, if you standard linear algebra, this when I multiply this, what happens? This x vector, which is a probability distribution, gets multiplied. You multiply this thing with this, it is like a dot product sum, right, that gets stored in this position, correct, yes or no?
First element.
Yeah,
First.
this thing, then this thing gets multiplied by this and so on, correct, and you again do the same thing, and then what happens here, those values that you get the vector that you get like this gets multiplied here, correct. So, then what would this be? If you unravel it, you would basically get this quantity, right, x I A I j m, the j thing is there, y j, correct, yes or no, x A I j, right, and this is, you keep j to be fixed outside, this is 1, it does not matter which order you take, but you agree that this will be something like this, right, that this means that you are doing this you are doing the multiplication between the x vector and the, this is not A, capital P, payoff matrix, right, and then each of those entries that you get, right, gets for each of the j's, they get multiplied by the corresponding yj value. Yes or no? The point here is we could have just read it right off there. This here, this xj aj quantity here, firstly we have only 2 people, 2 players. This is, instead of n players we have 2 players, right. This xj aj here literally is telling me what is the first player, telling me in terms of whether the first player has chosen, row player here has chosen the strategy vector x hat, and each of those individual values for the x hat vector tells me what is his decision, how much probability mass he has, like what is the probability by which he will play row 1, this is for row 2, row 3 and so on, right. Here we were summing over all possible realizable actions, right. So, over here all possible realizable action means what? These are all possible entries, this entry, this entry, this entry, all of these entries, right. Each of these entries give me an action profile. This means the first entry here tells me player 1 is playing row 1 and column 1 is, and column player is playing column 1. This one tells me what is this, second row, third column, right. So, this corresponds to the action profile of row player playing 3 and not 3 maybe, yeah 3, and the action column player also playing third column, right, third strategy, this sort of way. Okay. So, this is what this is, nothing more. Okay. So, this is the expected payoff for the row player, correct. So, naturally this implies that the expected payoff, I am writing this way, for column player for this same mixed strategy profile should be the minus of this, right, because it is a zero sum game, correct. Okay. Whatever this is. Yes, you can think of it that way, because you, it is like you have 2 matrices, one both of them entry wise they must add up to 0, right. So, the other way of thinking of this is would be, yeah, that for this particular action profile, whatever I store here for the column player, it should be negative of that. Okay. Yeah. So, there are, but basically it is the same thing, the negative value of the negative of this quantity. Okay. So, now all this is, now tell me, if we were actually playing this game, zero sum game, and I was the row player and you were the column player, how would we think about this game? Like, what should I do? Is there anything I can do that will give me, that will safeguard my payoff? Is there anything I can do Okay, let us ask a more basic question. Is there a dominant strategy in this type of a situation? What was a dominant strategy? It was a strategy that I can play no matter what others are playing, that will ensure me a certain payoff, right. That is at least good as anything else I can do, no matter what the others are doing, correct. If P is an arbitrary matrix, am I guaranteed to have a dominant strategy? No, right? Why? Can you give me an example, like a general intuition as to why that is?
Suppose for the row player, it will be like saying that there is a row in which every element is positive or something like that.
Okay, remember we also said something at the very first class, the precise values do not really matter, what matters is their relationship, like what you are storing in cell 1 versus cell 2 and so on and so forth, because any such thing, that generalized prisoner's dilemma game, I can basically do an affine transformation and convert all values that look a certain way to another game, but their relationship remains the same, right. So, all those things that prisoner's dilemma and so on, if I change the values, the game can still remain the same. Like I would argue about the game differently even if I write a different numerical value in terms of the sort of prison sentence. So, the point of this saying this is the following, that I could have, okay, so you can say that if everything was positive here, you want to say that it means that for the payoff matrix for the column player, everything has to be negative. That is what you are saying. Okay. But does that necessarily tell me that the row player always has a dominant strategy? So, usually such questions are answered by a counter example. So, you have seen a zero sum game where there was no dominant strategy, 2 player zero sum game where there was no dominant strategy. Okay, think about that and let me know. So, that is one thing. Okay. So, yeah, if the matrix is arbitrary and so on, I can't really say that there is a dominant strategy. So, naturally we know that okay, a Nash equilibrium is a reasonable this thing. So, and we know by Nash's theorem it always exists. Now, the question is we are trying to compute it. Okay. All right. Okay. So, now see, if I am a row player, I know that this is how my utility quantity looks like. Another thing to remember is, and I have sort of peppered this, sometimes the players know what the utility function of the other person is, and sometimes they may not know. Okay. When everybody knows all this information, it is called a complete information game and so on. But oftentimes in real life, and we will also study theoretical games where that information is not clear, that they do not know all the information about the utility of the other players, right. Because if they knew, they could do some computations on then, before the game starts and sort of think about what the game space is and what the other players are playing, right. Now, when we are talking about a zero sum game, that too between 2 players, this aspect of complete or incomplete information becomes moot, because the moment if I know it is a zero sum game and I can see my utility function, I can obviously compute the other person's utility function, right. So, here the incomplete and the sort of complete information setting does not have much of like it is the same thing, right. Okay. So, this is a basic point to remember for what we are going to argue now. Okay. So, the row player knows that this is how my utility function looks like. I will play, if I play a strategy x, a mixed strategy x, this is how my payoff function is. The column player will respond with some strategy y. So, in this case we assume this to be a sequential game. Okay. Let us think of it that way. That gives the second player actually a stronger some more additional power, because he can respond based on what he is seeing the row player doing, correct. In a simultaneous reveal game, I do not know what the other person, we are simultaneously revealing a strategy. Here whoever goes second can completely adapt their response based on what the first player has done, correct.
In that case, the probability distributions will be relative.
Yes, and how? So, suppose the row player has gone first. Okay. So, he has declared x. What should the column player do?
Column player should take the column player. Now, column player has only a row available. Column player should take the element with maximum weight.
So, is okay. Something like that. Let us see, is it true that the column player actually has a row available? What does that mean? So, when I do this x transpose multiplied by this payoff matrix P, what do I get? I get a row vector, correct? Correct? If I multiply this with this, I get a row vector, right? So, x dot product with the first column, x dot product with the second column, x dot product with third column and so on. That is how the matrix look, that is how the row vector looks, right. Now the question is, what should the column player respond with?
Oh, okay. So X is revealing the
Distribution itself, yes. When I say when it plays a strategy, it means it is the strategy itself is a distribution, right. So if I say I reveal this strategy, it means I have revealed the distribution, okay.
then more computation.
Okay, but what computation is required? Is it more computation? So let's so this is some type, this is basically a column 1 x not column capital P1 P2 and so on, right. The n columns, this is how this thing looks, and we are now waiting for the column player to respond. Column player strategy is basically, in general, can be a distribution over its own column choices, correct. So what that would mean is, he would add he would give some probability of choosing this entry, some probability of choosing this entry and so on, so that they add up to 1, correct. That is what a distribution is, correct, that all these yi values will add up to 1. Otherwise that is what a mixed strategy would be, right, it is a distribution. Now the point is that why does not the column player respond with the column, right, that gives it the maximum value? Sorry?
It is beneficial for the row player if it chooses the maximum.
Okay, all right. When I say maximum, yes, sorry, you are right. So the column player, so the column player knows that whatever I respond with, right, will contribute in this sort of a way to the. So this quantity that this middle I have written, it's basically telling me what each of these values are, right. It's the x transpose the pjth column, and then this is would be this value, correct. Okay. So yeah, so the column player knows that whatever value I respond with, this will quantify the amount of payoff that the row player gets. In order for the column player to maximize his payoff, it should minimize the row player's payoff, correct. So the column player should respond with an yj, rather a y, such that this entire value will be as small as possible. Yes, that is the strategy. Now if the column player went first, what should the row player do? So if the column player going first means column player reveals y, and based on that the row player goes second. So row player goes first, it reveals x bar, right. Column player's response should be argmin y right. It will try to minimize this quantity, because if it minimizes this, because this is a quantity that will go to the row player, if you minimize this, automatically it will increase the payoff for the column player. Okay. So now suppose the column player goes first, and it uses the strategy, mixed strategy y. What should the row player do? Yes, row player should try to maximize this quantity, right, because that is what is coming to him. So he responds with an x vector that maximizes this quantity. Okay. Yes or no? All right. So, people who are on who are listening over Zoom, is this clear? If you have any questions, please you may ask.
Yes, ma'am.
Okay, right. This is how anybody who is going second should respond.
We can't just pick the maximum element because it's just a distribution. We are not sure, like.
No.
which element.
Okay, fine. You are saying I'll pick one element, meaning I am going to pick. So, if the column player goes second, he will pick some column. That's what you are saying, right? Okay. Yes, they can do it. We'll come to it. But you agree, whatever column he picks, this should be sort of his guiding principle, right? Pick something so that this entire value comes down as much as possible, because that is a value that will go to the row player. It means a higher value, the smaller it is, a higher value will come to the column player, right? And if the row column player goes first and he reveals his y bar, row player can respond by picking some x that will push up this value as much as possible. That is why I have written argmax, okay? Among all possible distributions, let us write, okay, distributions, he should pick one, right? Okay. Now, what you are saying is correct. If there is a distribution, I might as well just pick a column j if the row player is going first, and the y player, the column player's response can be pick the jth column, right, such that this value is minimized. Why is this true? If there is a mixed strategy like y, right, why is that? Why can I extract the same payoff using a pure strategy? So, my question is, if I have a mixed strategy, so row player goes first, okay, he reveals his mixed strategy x bar. Column player's response would be to respond with a mixed strategy that makes this value minimizes this value. X is row player's first play strategy, and column player responds with y. P is the payoff matrix that has been that is already fixed. So, he responds. So, the column player should try to drive down this value as much as possible. So, he should pick a distribution such as y, right. Now, I am saying, why is it sufficient for the column player who is going second here to not even bother with a distribution? He can just come up with a column which is basically, columns are n, right, x p Ej. You know what Ej means, right? Standard basis. So, Ej is a vector where there is only one, so single one in the jth location, jth position, right. So, this means I am picking the jth, the column player is responding with the jth column, and you pick the j that minimizes this value. Why is this enough? Why? Is my question clear, people on Zoom?
The row player strategy is fixed.
Row player can like state it's a probability row player.
Yes, but once it has been revealed, you know exactly what this is, right? These values are all known now, right? Okay, so let us look at this, this entire expression, right? So, once x is revealed, I know what are these individual xi values. Pij was already known to me. I am a column player now. I can compute this entire thing. Now, you are saying, no, I need to do a mixture over my columns. Okay. So, now basically, and I will extract the one that will give me the best possible outcome, meaning I am going to drive down the value of the row player. Okay. Now, whatever that y is, this y, okay, his response, the one that minimizes this, okay. I look at it, I look at the positions where it is non-zero. if the value here is 0, it means I am not even playing this, I am not even picking this column, right. So, it is not giving me any value. So, I can just ignore it, I am just looking at the columns that are in the support, right, looking at the entries that are non-zero. It means those are the columns I am playing, right. Now, among those columns I can check individually which one gives me the lowest payoff and dump the entire probability mass onto that. If there are two columns, right, one helps me bring down the value more than the other, then what is the point of splitting the probability mass between the two? I might as well move all the probability mass from that lower payoff from the second one onto the first one, because I am just trying to drive down the value as much as possible.
Okay, in minimization.
Right, because x is known to me. So, once x is known, this all these xi pij values, these are all individually known to me, right. So, now what is the problem I am trying to solve? It is like these values are known to me, this row vector is, this thing is known to me, and now I am trying to find values to place here that will minimize this thing.
And what if Pij is negative?
What Pij is negative? So, then put higher, meaning some Pij is one entry, right. But here I have the jth and the, let us call it the tth entry here is basically x with a dot product with the tth column of the payoff matrix, correct. That is the value.
Can you repeat?
Okay, okay, let us. So, do you agree that if I know the x vector, which is the row player strategy, it is a sequential game. So, the row player has to go first, he plays his strategy, he says, he tells me or gives me a probability distribution in this vector form, which basically says what is the probability mass for the first row, probability mass for the second row, etc., right. Now, the payoff matrix was already known to me. Column player who is going second, his job is to choose a distribution y that drives down the payoff of the row player as much as possible. This is why we are picking a distribution y bar that minimizes this quantity, right. Now, I am saying instead of choosing a distribution, a mixed strategy, the column player can just merely respond with the column among the m columns that are n columns available, respond with the one that minimizes this value. This is just saying you pick the j, it is like the column player is not playing a mixed strategy anymore, it is playing a pure strategy, and its choice is that column, the action corresponding to the column that minimizes this value. Okay, because if there were multiple choices for this column, it means what? Choose any one of them. Like, why would you even mix? If you know precisely what the row player is doing, you can compute explicitly x transpose A column 1, x transpose A, sorry not A, payoff matrix E2, etc., right? Yes or no? See which is the smallest of these values, because one of these value which see which is the smallest value, and corresponding to that value pick that column.
It's like there is a EJ which will attain the minimum.
Yes, and why is that? That's like when I am mixing things, it might be, well, I am, let us say half and half, let us say 1/3, 1/3, 1/3, okay. So, there are three strategies, I place a mass of 1/3 for the first strategy, 1/3 of the second strategy, and 1/3 of the third strategy. Now, the point is, because I know this x times Pij, because the x vector is known to me, I basically know that the fact that I am placing 1/3 probability on the first possible action how much of that weight will actually come into play, because it will get multiplied by the first entry of this vector, right. The mass that I am putting on the second column will get multiplied by the second entry of this, and so on. So, among all these values, I see the one that is smallest and choose only that corresponding column.
Okay, so it's like minimum will be less than average.
Yes, right, because these values are explicitly known to me. So, I can know that exactly this is how much the contribution, if I put any non-zero probability mass, that will get multiplied by this quantity. Probability mass I place on the second column will get multiplied with this quantity, and so on. So, I see all the values, see which is the smallest, right, and just put all the probability mass on that column. Taking a weighted sum cannot be less than that, because that is literally the smallest entry. Okay, that is what this is. It is not hard, just it's okay. So, now similarly, if the column player goes first, the row player responds by picking a probability distribution which maximizes this quantity. A similar argument would imply that this guy should basically pick the row, right, EI transpose, which maximizes this value. Same argument, right. Okay. Now, I need some space.
So to ma'am,
Yes,
so to goal is either maximize it or minimize.
depends on who is the player. So, for the row player, the job would be to maximize it,
Yeah.
and the column player tries to minimize the row player's outcome. Why? Because he knows whatever, it is a zero sum game, right. So, whatever the row player gets, he will get the negative of that. So, the smaller the payoff of the row player is, higher will be the payoff of the column player. Correct?
Thank you, ma'am.
Yes? Okay.
Yeah, thank you.
Okay. So, this is why we are basically the entire game, instead of two people trying to maximize their benefit, what is happening is these two players are converging on the same object, the sort of a same game, in which the row player is trying to pull up his value and the column player is trying to drive down. That is the tension, that is the game here. How to come up with these vectors x and y, so that the row player's goal is to pull up the value as much as possible, and the column player's is to drive down. Okay? All right. Now, notice one thing. The point of writing this, what is it? Okay. Are we done? When did we start? Dear God. Okay. All right. So, I am going to take a little bit more time, but I need some more space. So, the row player. So, okay. So, whoever goes first is at sort of a disadvantage, because he does not know anything. So, he kind of has to play a mixed strategy. The whoever goes second can play a pure strategy, literally, because he can adapt his choice to what the first player has done. Okay, that is the point. We do not know if for the first player at all, it is not at all clear for any arbitrary game whether he can actually play a pure strategy. It is not clear at all. He kind of is forced to play a mixed strategy, because he does not know what the other person will do. The second person who is going second is always at an advantage, because he can adapt it, and therefore, he can play a pure strategy. So, think of it that way. Okay? But what von Neumann's theorem says is that no matter whether you go first or second, the first player can also guarantee a certain outcome for himself if he plays the right mixed strategy. So, if the row player goes first, if he understands this game, this thing, that the column player will always try to respond with this, he should try to do this calculation ahead of time. He should actually pick an X transpose that no matter what, which column the column player comes up with, it drives the value as much as possible, right. And the column player, if he goes first, should know that no matter what I give y, the row player is going to pick a row that will drive up the value, because that will be his payoff. So, he should pick a y that brings down this value as much as possible. Okay. So, this is the thing. So, the theorem is, this is the first player going first, the row player going first, min X transpose P y is equal to min max, okay, I can see it this way maybe, X transpose P y. Okay. So, this is that famous Minimax theorem. Now, there are many other Minimax theorems in game theory and just general optimization, which have this sort of a flavor, which looks like this, but this is the, when we say von Neumann's Minimax theorem, this is what we mean. So, this first quantity, this is an equality here, basically is saying the row player is going first, row player's strategy is always indicated by X, the column player is going second. So, as we just discussed, the row player should do this calculation ahead of time. He should always give an X transpose that no matter what the column player does, in particular when he tries to respond with a Y, this will be his outcome, this left hand side. Now, when the column player goes first, he does the similar calculation, but from his perspective, he should choose a Y that no matter what this guy responds with, right, the column player, row player responds with, will always minimize this value, because this value indicates what the row player's payoff will be, and the column player's payoff is a negative of that. So, he is trying to minimize it. Okay. Now, instead of this, we know that the column player's response, okay, I have to make some space, I will just continue writing here because everything is kind of here already. The left hand side is what? Max min, I am just plugging that value, okay, j X transpose P E j, right. Right hand side is min of y max of the row X E I transpose P y, correct. This is what we just now argued, right, all right. So, notice this is a, now we will use linear programming, this is that. So, left hand side, I am just going to write it here, min of j a E j, right. This is when row player goes first, right. Right hand side represents the opposite situation when column player goes first, not capital A, E okay. I have just repeated what I wrote before, nothing more. Now, I look what this means here. So, let us write, let we define this quantity, okay. X transpose this quantity here, think about this x transpose p of Ej. This we are saying across all j's we want a value that v is a variable that tracks this quantity. Okay. So, x transpose p Ej, correct, for all j. These are the column entries, correct. Now, if I open this x transpose p of Ej, do you know, can you tell me what this is? It is basically just xi p ij, where you are just running over the indices, the rows. Okay. This is exactly what this is. So, v is a value that it is a minimum, the ideal value of v is when it is v has to be smaller than all of this, because v is basically the minimum of this. So, I can write this as minimum minimize v such that v is less than equal to this quantity for all j n, correct. We also know that summation of all the xi is actually equal to 1, because x is after all a probability distribution, correct. Each of the xi's are between value 0 and let us say greater than equal to 0. I do not need to write less than equal to 1, because this constraint already takes care of that. V is a value that is at most this one for each of the j's. So, all I can say about v is it is a member, it is a real number, correct. I do not know whether it is negative, positive, anything, right. Okay. This is what I extract from the left hand side. From the right hand side, what is the corresponding constraints that I can pick up? It is the same thing. Let us call this max of w. The variable that tracks this value is w. Okay. So, w is greater than equal to ei transpose p y for all this. So, this quantity is nothing but ij yj, right, n, correct. So, w should be at least as much as this for all of the rails. Again, yj is a distribution, y is a distribution. So, the entries must add up to 1. Each of the yj's are greater than 0 for all j n, n, right, and again w is just a real number, correct. Yes or no? Yes? I just wrote these things down here, right, just nothing more. Now, notice something. Is this do you recognize this and this as something that you have seen before? This v is at most x transpose p of Ej. Sorry, Mona, I didn't understand. Yes. What is wrong here? So, P, the matrix P multiplied by the vector E of j will leave behind only these elements. So, that is why. So, this j is this j and the summation is over the coordinates of xi. Okay, so, it's if you write down the matrix, it is a matrix multiplication. Okay. So, yeah, and here I is this I and j is the running sum. Okay. All right. So, do you recognize this as something that you have seen before, these kinds of programs? Is it a linear program? What is the main definition of a linear program? Bunch of constraints, I agree, but the linear program requires a linear set of the constraint should be linear, right. So, is this a linear constraint? It is linear in what? If it is linear, you have to tell me linear in what? Correct. it's linear in the mixed strategy of the row player xi. Pij's are coefficients basically, they are behaving like constants, right. So, this is a linear combination of the xi value of the xi's, right, the mixed strategy. Similarly, this is the same thing. Obviously, this is a linear constraint, right, it is just a summation of the values, linear constraint and so on, right. All right. By the way, linear programming does not say anything about what the objective function should be. Objective function may or may not exist. The linear program is you need the linearity over the constraint space. So, just to keep this in mind, because a lot of students seem to think that even the objective function has to be linear, else you can't be. Okay. So, now what do we know about such programs? If you do not know this before, we know, okay, first and foremost, can you say something between this and this? Like we have to show equality, right? Is one of, so one way of showing equality is showing inequality on either direction, right? So, is there one of this, one of the direction, is it obvious? Based on whatever we have discussed, we already have discussed one of the inequality. See, over there we talked about, this is when the row player goes first, he comes up with a x transpose py, right, this is his payoff. When the row player goes second, this is his payoff, right. Yeah, okay. So, sorry, here when the row player goes first, this is the payoff.
Ma'am,
Yes.
I have a class at 5.
Okay, you may leave. I'll just repeat this maybe next time a little bit. Okay, let me just finish it, then and do watch the video towards the when we post it. Okay, and if you don't follow, you can ask me. So, this x transpose, this says the row player, this is the payoff of the row player when he goes first. This is the payoff of the row player when he goes second. We have already said that going second give me no disadvantage. So, when the row player goes second, its payoff can only be at least as much as when he goes first. So, the inequality in this direction holds from what we have discussed here, right. So, we know that max is same, is at most right. So, this is already known. So, to prove equality, I just have to show the other direction. Okay. So, here let us call this a primal program. If you know LP duality, if this is a primal program, it is a linear program, anything can be a primal program, does not matter max or min, it has a corresponding dual linear program. This is what, for this is what it would look like. See, I did not use that to derive this, I derived these two programs based on our basic arguments about row players and column player, two player zero sum game. It just so happens once I write this down, you see that this is the relationship. Okay. This argument also does not involve duality theory, it is just basic argument about zero sum games. But now to show the equality, we basically now invoke the strong duality property of linear programs. Strong duality says the optimum solution for the primal and the optimum solution for the dual have to be equal. Okay. So, this is what makes this quantity optimum primal is equal to optimum value of the dual. Okay. So, and moreover, think about this, this is where the optimum meets. Okay. The maximization problem, in this case it is our dual, is trying to go as far as possible the minimization problem is trying to push it as much as possible. Where they meet is where the optimum value is. Okay. So, using that, what can we say? That they are equal here. When they are optimum, they are equal here. But what about the other direction? Sorry?
Dual is less than the prime.
Dual is less, okay. Dual is this. This is my dual, right? The maximum, usually it's the, okay, fine, it doesn't matter. I've written this is where. This is the dual part, this is the primal, okay. Yeah. This is the V variable and this is the W variable. So, strong duality says that they will actually be the same thing. So, when both of them are playing optimally, the value of these two programs will be the same. So, the rho players, this is why, okay. The other thing also holds, okay. Okay, I am just going to say equality holds for star. Now, notice something, what that equality is saying is that as long as both of them do the right thing, which is argue in the optimal way, this is the value, whatever this quantity is, the numerical value is the value that rho player is guaranteed to obtain. Okay. The negative of that is the value that the column player will obtain. Okay. So, not in generally games do not necessarily, so they add up to 0, that is the point here, okay. And in some special games this value is 0 basically, both of them get 0 values, but in general it does not have to be true, okay. So, and this proves the Minimax theorem. Now, I really ran out, I did not. Now, let us just quickly, okay, do not want to rush it maybe. Do you all have any questions regarding what we did so far today? Next week I am not going to meet you on Wednesday, but I would like to teach a longer class on Thursday. Either we start early or we continue. I am going to ask because they have class after this, right. So, do you all have any questions regarding what we did today?
So, do we assume efficient computability of US?
Good, okay. You tell me, are these calculations doable? Which part is not doable? Think. If you knew x, if the rho player was, you are the column player, this can be computed, right. All you have to do is do x transpose, you multiply x, the vector x with the P matrix, you get these values, and then from there you can find the column that minimizes the score, right. That you can do. If x is known, you can do this. Similarly, if y is known, rho player can compute this, right. So, the question is, how does, when the rho player is going first, how does he come up with this distribution, right, x, so that he is guaranteed to get some value. That is the question, right, because a probability distribution, computing a probability distribution, it is not at all clear how to do it, because it is basically telling me put some numbers over n variables if there are n possible actions, right, where such that they add up to 1, and depending on what those values are, my payoff will depend on that. So, I can agree that the finding of this distribution x, how rho player comes up with x, whether or not he comes up with the optimum value or not, that is not at all clear how to do it efficiently. But once x is fixed, whoever goes second, his job is easy, right. Now, primal dual theory says linear programs are polynomially computable, and you can find not only a feasible solution is one which will satisfy the constraint, but not necessarily give you the optimum value. Optimum solution is one which is feasible as well as satisfies this objective. For this it would be minimizing this v value, and for this it would be maximizing this value, in addition to being feasible. We can solve linear programs efficiently, which means we can find optimum feasible solutions efficiently. And that is why this game, the Nash equilibrium, okay, this game is solvable in polynomial time. These computations can be done in polynomial time. Even if I think in terms of just finding distribution, that may seem hard, but because of LP duality, because of linear programming, the mathematics behind linear programming, and because we know how to solve it efficiently, we can compute that also. Okay. So, it is not about just finding a distribution like needle in a haystack situation, it is basically solving these two programs. Okay. Now, the question is, what does this have to do with Nash equilibria? So, tell me, what does this have to do with Nash equilibria? The original question was to compute Nash equilibria, right? We analyzed a zero sum game and said this is optimal behavior, that the row player, even if he goes first, can guarantee a outcome like this. Column player, even if he goes first, he can also guarantee a certain outcome, right? That optimum value is this quantity that we found. So, what does this have to do with Nash equilibria?
Ma'am, this max-min value is the Nash equilibrium payoff.
Yes. And why? Can you just say why is that the, I guess I have already said it, but okay, say that again. Why is that the Nash equilibrium payoff? I mean, use the definition of Nash equilibria to answer this.
Yeah, so suppose for the row player, given the choice of y for the column player, x is the optimal choice.
Yes.
He has no motivation to deviate.
Correct. Right. So, that is the idea, that x is the optimum choice no matter what so from even if the row player going first, what is he saying? X, I know how to compute x that will guarantee me the best possible outcome. That has to be a Nash equilibria, right? The column player, nobody has any reason to deviate from this and extract a better outcome, because these two games, the primal dual, are saying that this is where the best value is. So, if this is the game that the row player is, the column player's answer is this thing, right. So, he is already choosing this, so that it drives down the value of the row player. So, he has no reason to deviate as such, correct. Row player is choosing an x transpose, so that this value is high as possible. So, this quantity, the feasible solution, the optimum solution, this quantity, the x and y values that such that x is feasible for primal, y is feasible for dual, and they are basically and let us call this the V star, okay, the optimum value, such that V star is x transpose P y, okay. This is the optimum value. This together constitutes a Nash equilibria for the game. Okay. So, now you can have multiple different such strategies. You can have a x bar, y bar, you can have x2 bar, y2 bar, all of them will have the exact same optimum value, and all of them will constitute a Nash equilibrium.
What did you say?
So, there can be multiple feasible solutions for a program, right. A program can have multiple optimum values also. So, there can be, I am not saying that x bar, y bar is unique, right. This is a paired situation. X bar is the optimum solution, x bar and y bar together are constitute the strategies chosen by row player and y player, such that V star is the value for this, that equality quantity, okay. That is the optimum value. So, all such pairs x bar, y bar that attain the optimum value constitute a Nash equilibrium for different games, you can have multiple different Nash equilibria. All of them will have the same value. We saw some games in which there were multiple different Nash equilibrias and they had different values, not here. Okay? All right. Interestingly, okay, so I am going a little slower than I thought. So the separable game is rather straightforward if you understood all of this. Okay, so since they are not here, I don't want to go over it. We'll start with the separable game next week, and then we will want to take pictures maybe. Okay, so then we will talk about separable games and maybe symmetric games also, and then we will move on to the computational complexity of computing Nash equilibria. Okay. All right then, if you don't have any questions, if none of you have, then this is it for this class.